Okay then, just another video on similar triangles. This time we're going to deal with triangles within triangles. So, again, we've got that key statement that we need to apply the mathematics that we're about to apply. The triangles below are similar. If it doesn't say that, then you can't use the mathematics I'm about to use, okay? If I look at this first one here, hopefully you can see two triangles. We've got the smaller triangle here, and then we've got the bigger triangle on the outside. To link it to what we've done previously, what you actually want to do is just draw out the two triangles. So at the side, the first step I'm going to do is just a very rough sketch, my smaller triangle and a bigger triangle. Okay, so if I concentrate on the smaller triangle, the sides are probably quite obvious. We've got 10 for the base and we've got 16 for the diagonal. With the bigger triangle, it's maybe a wee bit less obvious because we have part of the longest side, the diagonal, is x. However, if you just think about this side as 16 add on x, we just don't know what x is, we can write that out as 16 add on x, and the base, the bit along the bottom, would be 15. And that basically links it to exactly what we did yesterday. Now, with these questions, you just want to start off, like I said, the same way we did yesterday. So let's work out whether it's a reduction or an enlargement. Well, I've got all the information I need on the smaller triangle, and I need the longer side on the bigger triangle, so it's an enlargement scale factor, so ESF. Now, what that means is it's going to be large over small for the enlargement scale factor. Now, some people are maybe struggling to work out what sides go together. Well, you want a like side. So what I mean by that is two sides that are the same on both triangles. So in this example here, you can clearly see we've got the base and we've got the base. So we're going to use the bases of both triangles to get the enlargement scale factor. It's going to be 15 over 10. We can simplify that down, divide top and bottom by 5, we'll get 3 over 2. You might have a calculator for this, you might not. Okay, but we'll work through it as if we don't. Okay, so if we can follow that process through of what we did yesterday, the next thing we would do is we would say, right, the smaller sides, which is 16 times the enlargement scale factor, which is 3 upon 2, would equal the bigger side. This one's a wee bit different in the sense that we've got an expression for the bigger side, which is 16 plus x, but we can still put that into our formula. So again, just to run that through, the enlargement scale factor times the equivalent side on the smaller triangle gives us the bigger side, or the diagonal on the bigger triangle. And now all I'm going to do is work all this out. Now, 16 times 3 upon 2, that's the same as 3 upon 2 of 16. So divide by the bottom times by the top. 16 divided by 2 is 8. 8 times 3 is 24. Equals, and we've got 16 plus x, and we've now got a very simple linear equation that we can solve for x. Take away 16 from both sides, and we're going to get x equals 8. Don't forget your units, it's 8 centimetres. And if we look at the diagram, okay, it's not a perfect diagram, but it kind of fits with the data. We would expect this length here to be smaller than this length here. And again, looking at things in the diagram, it probably is going to be similar to 10, but less than 15. So 8 tends to fit with that. Okay, so if I move on to the second one, again, we've still got a triangle inside a triangle. It's just a slightly different setup. But again, I do have two triangles. So my first step is going to be to draw the two triangles. Okay, so quick sketch, bigger triangle, and then the smaller triangle there. Okay, so marking everything on the bigger side, I've got y and I've got 42, and we're dealing in millimetres this time, and in the smaller triangle I've got 10 and I've got 12. So this is actually going to work out to be a wee bit easier than the first question we did. It's now identical to what we did yesterday. Okay, so again, first thing we need to do is work out whether it's an enlargement or reduction. Well, we've got the two sides in the smaller triangle. I want the height of the bigger triangle, so it's an enlargement scale factor. Again, we're looking for a like sides to work to get the enlargement scale factor. Well, we've got the base on the bigger triangle, we've got the base in the smaller triangle, so I'm going to use that to find out the enlargement scale factor. Big over small, because it's an enlargement, so 42 over 12. And again, we don't necessarily need a calculator to work with that fraction. We can simplify it, divide top and bottom by 6. and we actually get a nicer fraction there, and we could now work through this without a calculator. Okay, so again, if we go to the formula, it's the smaller height times the enlargement scale factor, and that's going to get me what the bigger height is. And like I said, this one's a lot more straightforward, a wee bit more straightforward than the previous example, because I don't have an expression for the side I'm trying to find, I just have a letter. So like I said, it ties in exactly with what we did yesterday. Okay, and then again solving that, 7 upon 2 off 10, divide by the bottom times by the top. So 10 divided by 2 is going to give me 5, 5 times 7 is going to give me 35. Or another way to look at it is you can just do your fraction multiplication, okay, divide by 2, and then just multiply the tops and multiply the bottom. Either way, you're going to get 35 millimetres. And again, that ties in with the diagram. It's obviously going to be bigger than the 10 this side here, and it looks like it's probably going to be bigger than the 30 as well, so 35 seems to fit. Okay.